Kamalika, when the meeting formally starts at 4 o'clock, then of course you have to, Professor Kak has to say it. I mean, officially, these are all we are meetings.
Yeah, I understand.
Yes,
I understand.
you have to say more about. Yes, we are waiting because they just we are testing how the things are. Others will join.
I'll join in another 10 minutes, right?
Huh? Yeah.
Okay.
Okay, please take care. Okay, we are waiting for.
Sure. I'll join.
It is all right. It is set. I can see Professor Claudio Paolini has also joined. Most probably, yes. You can check.
Hello, good afternoon. Good morning. Good afternoon for you.
Yes. Good
to
afternoon.
see you.
Hello, thank you. You have joined. So nice.
I cannot stay so long, but just to
yes.
say hello to the group and congratulations for the event.
Hello. And yes, thank you. So plus Professor Claudia is all he'll come. Yeah? Yes. On time he'll come. Right. Professor Raghavan. Hello, Professor Raghavan. Professor Raghavan. Raj Singh ji. Hello. Professor Raj Singh. Dr. Raj Singh is he's from IPR. One of the conveners of this program. Yes. Mr. Raj Singh, yeah, hello. Kamalika. You can see him, Dr. Raj Singh is there. Okay. Yes. So we'll start now, not now, after some time. Yes. We're going to start. Fine. Hello. Hello. Pankaj is there. Hello. You are not audible, Pankaj.
Yeah. Now I think you can.
Is there?
Now you can, I think.
Yeah. And I can see Professor Subalkar is there. Hello, Professor Subalkar. He's there. Professor Subalkar is there. Yeah. Partho is there.
Yes.
Professor Partho is there. Yes.
I am audible.
Yes, you are audible.
Hello, sir. Hello, sir.
Professor Raghavan is there. Yes. Yeah. So many already 30 persons have come. And the meeting is going to start at 4 o'clock after 5 minutes. So thank you.
Hello, sir. Dr. Raj Singh, very happy to see.
Karthik is there? Professor Karthikeyan? MB Karthikeyan? Hello? Professor MB Karthikeyan?
No, sir.
I cannot see you, Professor Karthikeyan. Professor MB Karthikeyan.
No, sir, he is not there.
Okay.
Dr. Ruth Jensi, welcome.
Thank you, sir. Yes, sir. Thank you, sir.
Sir, Basu sir, Dr. Mahadevan also joined from Bangalore ISRO. Professor V. Mahadevan of ISRO has joined, many scholars have joined. There are some people from Abu Dhabi.
Good afternoon, Professor Raghuvar.
Hello, sir. Very happy, sir.
Very happy, and then congratulations to a student for having had a great this thing. I'm sure he'll be very successful in his attempt in US.
Sir, Dr. Basu sir, he is talking about Krishnagant, who is going to US.
No, he is an extraordinary student, no doubt about it.
Madhusudan, Kavana, you're all welcome.
Sir, happy Sankranti and Pongal.
Oh, thank you.
To everybody.
Dr. Vishal Kesari, your proceeding is simply superb. I am going to make it as a book.
Yes.
Thank you very much, sir.
I will make as a book and send it to you. Send one to Dr. Raj Singh, one to Dr. Basu, one to you. It has come out very well.
Okay, thank you. Thank you very much, sir.
Who helped you in typing, sir?
Actually, the typed matter we get from contributors only. We just edit and give it saved.
Okay. Dr. Mahadevan also appreciated it very well.
Definitely good. I had to read through in detail. I had to go through in detail, but it was very good.
Yeah, thank you.
Professor Subalkar wants to know whether he is audible or not. Yes.
Very feeble.
Hello?
No, sir, he is not audible.
No, Shunachina.
No. He's not audible. Hello.
Sai Kiran, welcome.
Yeah, good afternoon, sir.
ना audible तो ना है तुम्हें
Dr. Jain Joshi, welcome.
Hello.
Yes, sir. Thank you.
ना आपने तो audible ना है थोड़ा देखना पड़ेगा.
So just 1 minute, sir.
तेरी है करे तो एक ही होता है.
Namaskar to Dr.
Sir, just 1 minute.
Hello, namaskar, sir. Namaskar.
Sir, very happy to see you, sir. Dr. Shivagankar.
Yeah, thank you, sir. Thank
It's
you.
a great blessing, sir.
Back in DIT Pune in the guest house.
Okay.
Sir, Dr. Basu, sir, Dr. Shivagankar has joined. Okay, sir.
Hello, Dr. Vasu. Namaskar.
Yeah, hello, namaskar.
Professor Shivagankar, namaskar.
नमस्कार है काक साहब कैसे हैं? अरे कहाँ हैं आप? यूएस में कि यहाँ?
नहीं यहीं पे हूँ.
यहीं
पे हूँ सर.
अभी यहीं पर है.
अच्छा गुड.
अभी यहीं पर है.
आप तो घूम करके आ गए.
हाँ हम तो मुंबई में आ गए अभी.
Yeah. But I think it's quite cold in Bombay now.
Yeah. Last 1 week it is unusual, you know.
Yeah, that is what was more surprising. One of my friends called yesterday and I said, yeah, I envy you. You are having such a beautiful weather and we are there. No, that is not true. We are having quite a bit of problem here also.
Yeah, we require blanket in the night, which is not very common in Bombay.
Correct.
Sri Charan, welcome.
Good afternoon, sir.
So thank you, Dr. Raghavan, for invitation.
No, it's a great.
Yes.
We are all very proud, sir. Blessed that you are joined here.
No. It's a great occasion.
I wish Dr. B.N. Basu tell the junior scholars about Shivagankar.
No, there is nothing much to tell actually.
No, there are scholars come from different parts of the country. They should know about you.
That is the modesty of Professor Shivagankar.
Yes, very much.
Harshmital, welcome.
Good evening, sir.
Sir, just wait for 1 minute. There's some technical problems there. Okay.
Hello, Komalika is there?
Sir, there's some problem with Komalika's machine. Just wait for 1 minute. Okay,
and then we can.
Komalika, you just come and just tell from there.
Hello.
Just come here.
Prasanna BIT, welcome.
ठीक है कोई असुविधा नहीं.
Sir, good evening, sir. আমি আপনার মেল আইডি দিয়ে করছি। Sir, with due permission, may I start?
Just. There's some problem in joining. See, Dr. Suvalkar left, and then now it is more than 100 participants, so there is difficulty for him to rejoin.
Okay.
So yes, you sort out this problem. Professor Suvalkar wants to join.
Shomadi,
yes,
YouTube link. Share the YouTube link so that everyone can join.
Yeah.
Share the YouTube link. WhatsApp group. No, in this message group, just share. Huh?
Hello. I have a suggestion.
Sir, yes, sir. We have number of participants. The participants have increased more than 100, so it's not possible to join in the Google Meet. We have shared the link, the YouTube link.
Yeah. In the meantime, I have a suggestion.
Yes, sir.
I have a suggestion. Let Purushottaman give his first lecture. Okay, and I think Professor Parthapratim is there. Professor Sarkar.
Dr. Parthapratim Sarkar, sir.
Yes, I'm here, sir. Yes.
Okay. So let Purushottaman start giving his lecture. It's my suggestion. We cannot wait.
Okay.
There's some problem.
Sir, we may start.
You may
sir,
start
with your
on the
permission,
lecture.
may I start, sir?
The first lecture could be by Purushottaman from Lancaster. Okay, from Lancaster. All right. Because there is some difficulty in joining, from the side of Professor Suvalkar. Okay, please let us start on time.
And Dr. Basu sir, Dr. Shivagankar may be leaving in half an hour. You want to tell anything about him?
Yeah, Professor Shivagankar, nothing to tell. He's only to tell that he is Professor Shivagankar. Nothing more to say. Okay, nothing more to say. We are really proud to have him in our midst. And thank you, Professor Raghavan. It is possible because of you only. See, we know what he is. So I cannot say anything more than that. Everybody knows about him. Thank you, Professor Shivagankar.
Thank you, sir.
And yes, I will. Kamalika.
Yes, sir.
Yeah, I think.
Sir, may I start, sir, with due permission?
We can start.
Okay. Thank you, sir.
And also, during our start, Professor Shivagankar may say a few words because he's technically expert. We are not so much. And one thing, if Professor Suvalkar can come in the meantime, fine. Otherwise, let the program start with a lecture by
Dr. Purushottam.
From Lancaster. Okay, let us go ahead then.
Okay. Thank you, sir. Thanks. Good evening and welcome to you all. I am your host and moderator, Kamalika Tiwari, on behalf of R&D Cell, Dr. B.C. Roy Engineering College, IEEE Student Chapter, and the Thinkers, and from the Thinkers in Vacuum Electronic Devices group. I welcome you all on today's webinar on metamaterials and their application encompassing assistance in microwave tubes. So we have seen that over the past 7 decades, the performance improvement of microwave tubes has remained the prime objective of the world vacuum electronic community. So it has become a matter of interest to explore artificial materials. So these materials, metasurfaces, the photonic crystals, the photonic band gap materials, electromagnetic band gap materials belong to the category of these artificial materials. Out of this enormous global attention from the from the researchers as well as from the end users all over the world for their improved performance in comparison with the conventional counterparts. So today's webinar, particularly on the metamaterials and its applications in the microwave tubes, plays a very important role. I welcome all the researchers, all our guest speakers on this platform. Thank you all for joining us. Now, I'll request Dr. Sanjay Pawar, Principal, Dr. B.C. Roy Engineering College, to give the inaugural speech. So, kindly.
He's not audible. Hello.
Yeah.
Not audible.
He's not audible.
Hello. Oh, sit. Okay, thank you.
Yes, sir.
No, it's not audible.
Sir, you are not audible, sir. Sir, not audible, sir. Sir, not audible.
Call him on phone.
Sorry, sir.
Yeah, call
Please
him.
call.
Call him on phone. Hello.
I think you must rejoin. You must rejoin with your audio on. Please rejoin, then only your audio will be okay. जोशी जी को मेरा नमस्कार. कैसे हैं सर?
Sir, you are not audible, sir.
Not audible. Not audible. Not
Sir,
audible.
you are not. Sir, not audible, sir.
Okay, let Purushottam start.
I am clicking the microphone on the right hand side, but why is it not coming?
Sir, you are not audible.
Kamali,
Sir, we are missing out your sir. We'll rejoin again. Sir, we will miss. Sir, okay. maybe there is some technical problem we are having from our end. So as with due permission of Principal Sir, Dr. B.C. Rai Engineering College Principal Sir, he is asking to go for the next program. Basu sir, we will go with
yes. Hello, can you hear me? Yes.
Yes, sir.
I think Professor, go ahead, please. Next.
Okay. Sir, this is a small message from our chairperson, Torun Bhattacharya, sir. He is not presently in this platform because of some oversight duties. So here's a small message from him, which I want to just call out. It gives me immense pleasure to know that the combined initiative of IEEE student branch, R&D cell Dr. B.C. Rai Engineering College, Durgapur, and Thinkers and Vacuum Electron Devices Group, India, is organizing a one-day webinar on metamaterials and their applications, encompassing assistance in microwave tubes in a befitting way. In the face of outrageous mayhem of COVID-19, for long 2 years, webinars and online educative classes have played a yeoman role in keeping the lamp of learning burning bright, including our group of institutions. My heartfelt greetings and appreciations to the organizers and all the eminent participants from far and near who are making this great event possible to happen under extremely adverse conditions. I am confident the deliberations made by the leaders of scientific community will go a long way to further enriching the storehouse of knowledge in this field and truly be useful for the service of the society. I wish the organizers all success. This is a small note that we have received from Tarun Bhattacharya, General Secretary, Dr. B.C. Rai Engineering College and Group of Institution. So now, thank you.
Yes, excuse
sir.
me.
Yes, sir.
I think now I am audible, right?
Yes, sir. Yes, sir. You're
audible. I've resolved the problem. Okay.
No problem. So I think you can load your. He can load your file also. Yes.
Yeah.
Go ahead, please. Yes.
Yeah. Just a moment.
Okay. So, due to unavoidable circumstances, Dr. Debashish Pal, one of our chairperson for the next 2 lectures, he is not available with us. But we are very happy, we are very glad to have Dr. Partho Pratim Sarkar, Professor, Kalyani University, who will be chairing the next 2 sessions. Now, I'd like to welcome our a small talk from Professor S.K. Kak, sir. Sir, kindly say few words. I'll request Professor S.K. Kak, sir.
Thank you very much. It's a great pleasure to be associated with something that has been a milestone in various areas. Microwave tubes have done a remarkable work, not only in earlier radar systems and other particular areas. We have lot of microwaves in our homes, whether you are using microwave heaters or whether you are using microwave cookers or whatever. So microwave is in the home, microwaves in our communication, microwaves are going to be very, very important in future in satellite communication or in other particular areas also. In defense, it has an immense contribution, both for identifying objects either in the air and now sometimes just in the satellite domain also. So working in the area of microwave, especially with the increasing frequency, increasing bandwidth requirements, increasing channel bandwidths, and at the same time being able to have more larger power, needs that the material search, the understanding of how materials behave under various particular conditions also is of importance. So metamaterials are probably some such material, and non-natural material, a scientifically designed material, a synthetic material that can be tutored or that can be tailored to certain specific requirements of permeability and permittivity. So the beauty of this particular material can be harnessed for microwave devices in various particular areas, and even in case of antennas, in case of devices that are used as oscillators, as amplifiers, as devices that can have a larger impact in terms of other applications. So I thank the organizers for taking up this topic. I think India needs to work in these particular areas, and international collaboration in these areas is very, very timely, very, very important. The learned people who have devoted their lives, I know Professor Basu, who has devoted his whole life to microwave tubes. I know other particular people who have enormous contributions in this area, and it is the right time to consolidate that particular learning, to consolidate that particular knowledge into some products and into certain particular areas specifically that will promote not only harnessing that knowledge, but converting it into patents, converting it into technology that can be sold not only for in the country, but all over the world. Second thing that I would like to share is that when we are talking in terms of using materials which can be tailored, these particular kind of materials at the present moment have got some one kind of material embedded in a matrix, and therefore its property can be changed. We need to understand that there is a certain amount of interest today in areas where such particular thing can be embedded in the biological samples in order to do some more higher order things within the biological systems. That is another particular area where this kind of work can be important. I do not know how much amount of this thing is interest is there in that, but I believe there is a certain amount of requirement of that kind of work. With lastly, I again thank you all for inviting me and for giving me the pleasure of being part of your this webinar. And I'm keen to listen to the experts, keen to listen to their research outcomes, and keen to listen to what will be the deliberations of the seminar. Thank you, and I wish all the success to the seminar. Thank you.
Thank you, sir. Your words are really enlightening, and we are very happy to say that we have a large number of students, research scholars, and faculty members. We have scientists and industry persons. We are attending this event today, and thank you, sir, for your words, sir. Now I'll request Professor Pankaj Chaudhary, sir, Editor-in-Chief of Journal of Electromagnetic Waves and Applications. Sir, we are eager to hear from you. Over to you, sir. Sorry, sir, you're not audible. Sorry,
Thank
sir.
you very much. Thank you very much.
Okay.
Okay. Hello to everyone. Very good evening to you all. Before I say something about the webinar, I would like to record my heartfelt respect and affection for my revered teacher, Professor B.N. Basu, who has always been my advisor on my personal and work matters. I am thankful to him for inviting me to deliver the opening speech. Also, I keep Professor S.K. Kak in high esteem. I recall the days when I used to be associated with him during my work span at the Electronics Engineering Department of the IIT BHU. It remains definitely of immense pleasure to see you, Professor Kak, after a long time on today's webinar platform.
Yeah.
Dr. Sarit Paul, who is one of the organizers, also used to be in Professor Kak's lab. Nice to see you as well today, Dr. Sarit. Interestingly, no one is unknown nowadays, and the coordinates can be traced. And thanks to the internet means, which have now become so much indispensable in today's survival. And organizing webinars is simply one of the prime examples. Now, coming to the themes of the talks of today, those are pivoted to metamaterials, and Professor Kak really elaborated a lot on that. And to introducing the speakers of the day, the first talk, as Professor B.N. Basu mentioned, it will be by Dr. N. Purushothaman of the Lancaster University, UK. The title of his talk is Scope of Metamaterials in Microwave Tubes. Dr. Purushothaman used to be at the Siri Pilani before. And coming to the theme of the second talk, I think, the second talk is by Dr. Subal Kaur, who used to be a professor at the Institute of Radiophysics and Electronics, Calcutta University. His talk is entitled Metamaterials and Metasurfaces, an emerging field of research in microwave and photonics. Professor Kaur has the rare distinction of being a Fulbright scholar, apart from the other achievements he earned in the academic career. Interestingly, for the last 5-6 years, my own research has been in the area of photonic metamaterials. The subject matter is greatly interesting because artificial metamaterials have emerged and attracted increasing attention because of their unique properties that can be tailored. These may include nonlinear left-handed metamaterials, impedance matched near zero index metamaterials, say for example chiral metamaterials and varieties of other metasurfaces. The proper use of metamaterials provides key solutions to achieve exotic features of electromagnetic waves, or rather tailoring the properties of electromagnetic waves, thereby opening up the avenues for designing many technologically important devices with on-demand kinds of applications. Metamaterial-based tunable absorbers, sensors, tunable filters, metamaterial cloaks, etc. are some of the potential examples only. So within the context, I'm happy to say that recently a book was published by the CRC Press, which is a part of Taylor & Francis of the UK. It was edited by myself, and the book is on metamaterials, technology and applications. In this book, Professor Subal Kaur, who is one of the eminent speakers of the day, and Professor B.N. Basu also contributed chapters, apart from the other scientists from different countries. The interested readers may have a glimpse of it. With these words only, without further ado, I now hand over the floor to the lecture program chairs. I think they are Dr. P.P. Sarkar and Dr. Devashish Paul for further move. That's it. Thank you very much.
Thank you, sir. Thank you, sir. Before we proceed for the guest speakers, today we'd like to hear a few words from Professor Claude Paoloni from Lancaster University. Sir, I'll request you to say a few words today. So, I request Professor Claude Paoloni from Lancaster University.
I think it's not present in the meeting right now. So.
Okay. Thank you, Nalini. Thank you. So, as mentioned by Professor Chaudhary, sir, we are now ready to start with our speakers today. But before that.
Hello. Yes.
Hello.
Would like to, before you start, if you allow me,
Yes, sir. Kindly, sir.
We are not going to leave. Professor Shigaoka has.
Oh,
Raghunath,
okay,
he is
okay.
there, yes.
So, I'm really
think,
sorry. Now I'll request Professor Raghunath Shigaoka, sir, please, sir, to say a few words today on this topic. Shall I request you?
Okay, thank you very much. Actually, I was not prepared to talk anything. I thought I will listen. But I would like to thank Dr. Raghavan. He gave me a ring in the morning that there is a seminar which is on metamaterials. And Professor Basu has sort of said that I should be informed about it. Actually, metamaterials is something concept which is a really very, very revolutionary concept. Earlier, we used to depend upon the natural materials and many of their properties, like if you take photonic crystal kind of materials, the band gap of the material was almost sacrosanct, which used to come with the natural properties. Today, we are having a technology which really allows us to create artificial materials and manipulates all its electromagnetic characteristics, including the refractive index. You can go to negative refractive index, you can make it imaginary, you can change magnetic property, you can change electric property. And most fascination I got about this metamaterials was by the photonic crystal paper which was published earlier. We said that the colors on the butterfly wings are not the colors. And that was something which was mind-boggling, because we always believed there are beautiful colors which you see on butterfly wings. And it was like saying that now there are no colors on the butterfly wings. Why you see the colors are because of this photonic crystal effect, which is just a periodic structure which you see on the butterfly wing. So many of the words which we used to use in electronics earlier, like high impedance surfaces, Bragg kind of phenomena, they all were encompassed into this broader category, what we call as the metamaterial. So it is a really revolutionary concept which came, and it is now going to shape the world, as Dr. Kag also said earlier. So it is delighted to be here to listen to the vacuum tubes. Of course, vacuum tubes we have forgotten. I did vacuum tubes when I was a student in my undergraduate studies. And after that, I never studied vacuum tubes because most of the things were semiconductor. But it is good to hear about it and the application of metamaterials in the vacuum tube. So thank you very much for the invitation and giving me opportunity to speak in this. Thank you so much, sir.
I would like to say a few words, if you allow. Hello. Kamalika, I want to say a few words.
Sir, please continue, sir.
But those who are working in the area of microtubes cannot work without this book. You know this book. So this is my essay. This is Bible.
Thank you, sir.
Can you see this book?
Yes, sir.
It is a name. I sorry, may not be able to see. Yes.
Yes, sir.
Can you see?
Yes, sir.
Yes, it is.
Yes, this is.
Thank you, sir, for sharing.
This is the Bible of the,
Thank you.
Bible. Okay.
So this is used by all students.
Yes.
There is
He has written many other
this used by all students throughout.
Thank you, sir.
But so very clear and with so many examples in that.
Yeah.
So that is the greatness in that book.
Yes, in writing our books also.
Examples are given where you can follow it very well.
I also authored some books, but not without help of Raghunathji.
Thank you, sir.
It's a really excellent. We have at least I have used extensively, and I asked my students also to use.
You go ahead, Kamalika, please.
Yes, thank you, sir. Yes, sir. It's very nice to hear from Raghunath, sir. We have gone through his books, but now we are really very glad to see him on screen. Thank you, sir. Thanks, sir. Sir, it's a blessing, sir. Thank you, sir.
Give me some credit.
Yes, sir. Basu, sir, all credit goes to you, sir.
Thank you. Please go ahead.
Thank you, sir. So before we start with our invited speaker, we have Dr. Shubol Kaur, sir. The lecture session program chairperson will be Dr. Partha Pratim Sarkar, sir, from Kalyani University, who will be the lecture program chair. Who will be and we have the invited lecture talk from Dr. Shubol Kaur. A few words. He is known to us, but still, Professor Shorit Pal, sir, will say a few words on Dr. Shubol Kaur, sir. Over to you, sir.
Good afternoon, everybody. Dr. Shuvalkar is former professor and head of the Institute of Radiophysics and Electronics, University of Calcutta, India. His field of specialization is microwave engineering, metamaterials, and high energy physics. Dr. Kaur has 3 patents to his credit and published a large number of research papers in peer-reviewed international journals. He was visiting scientist to various universities and institutes in US, Europe, and Asia, including Lawrence Berkeley National Laboratory, US, Oxford University, UK, Cockcroft Institute, UK, Kyoto University, Japan. Dr. Kaur has authored a textbook entitled Microwave Engineering, Fundamentals, Design, and Applications, and contributed a number of chapters in book published by Elsevier, Springer, Nature, CRC Press, etc. Another book entitled Physics and Astrophysics, Glimpses of the Progress, is to be published in April 2022 by CRC Press of Taylor and Francis Group, and that book is in the press. He is the recipient of Young Scientist Award of URSI and IEEE MTT and Fulbright Award of US government. So may I now request Professor Shuvalkar sir to deliver his lecture. Sir, please.
Thank you, Professor Pal. Am I audible?
Yes, sir.
Okay, great. So I am indeed honored to be invited to deliver this talk to the inquisitive young minds and to the erudite audience. The title of the talk, as you can see, is Metamaterials and Metasurfaces, an emerging field of research in microwaves and photonics. Metamaterials and metasurfaces are the watchwords of the 21st century. In 2001, first successful metamaterial was fabricated in University of California at San Diego, USA, that could exhibit negative refractive index, a counterintuitive phenomena not available in nature. In the last 1 decade, the 2D or planar version of metamaterial known as metasurface has revolutionized the nanophotonics research. Initial developments in metamaterials was in the microwave frequency domain, limited by the fabrication technology available in those days. Most of the proof of concept for metamaterials developed at microwave frequency with many novel applications. However, with the advent of nano fabrication technology of today, the metamaterials and more specifically metasurfaces have opened up.
Sir, excuse me, sir. Slides are not visible. Slides.
Slides are not visible?
No. Slides are not visible.
Just a moment.
Sir, you have to share the slides.
But it says this call has reached join now. When I'm giving join now, yeah.
So there'll be a present now icon at the bottom of your screen.
Okay, I have joined. Now.
No, you don't have to join.
Actually, you have joined at 2 places. Sir, you got to control one. You have to relinquish.
Sir, from one place you have to present slide.
Okay, but
there is an arrow, sir. Sir, in the bottom you can see there are 5 circles, and from the second from the right there is an arrow. Just click there.
Why I cannot see that?
There is an arrow and there is present now. There are 3 dots. You can see there are 3 dots, 3 vertical dots.
Sir,
yes, sir. Yes, sir.
He has to first go out or stop this thing. He is sharing 2 devices.
Yes, sir. Yes, sir.
He has to go to one device only and share from there.
Yes, sir. Sir, please, you have logged on from 2 devices. Please switch up one device. From the same device, you have to go for presentation.
or he has opened two this thing from the same device.
Yes, sir. Sir, please log out from one device.
Should I enter a new?
No,
Yes,
no,
sir.
sir.
You go out and rejoin again, but not from two devices, but from single device.
Sir, sir, there is already 99, so he may not be able to rejoin. There is a problem, actually.
No, he will be able to rejoin.
Yeah, that is becoming the problem.
Because once he goes out, there will be less number, so he will be able to.
Yeah. That may be the case. Yes.
So I'm going out, huh?
Yes, sir. Yeah, now you can join. And share. Now join, sir.
He can't hear now.
Yeah, he's
Yes,
joining. Yeah, now you share.
So at the bottom there are 5 circles. That is the arrow. Just click at the arrow.
Pal sir, probably Subalkar sir may mail you his presentation and somebody from the organizers could share the presentation.
Yeah, it
No,
might
actually
be because of the fact that he is not able to share the screen.
Yes, sir.
He is not able to share the screen. He has to have the screen has to be shared by someone else.
Okay, sir, please mail the slides to me. Sir, please send the PPT to me, sir.
I think, hello.
Yes, sir.
I think in the meantime, let us probably request N. Purushottaman to share this.
Okay.
Otherwise, it will be delayed, you know.
Okay. That can be done.
Let us be practical. Let us go ahead.
Okay, sir.
Of course, that would have been better, you know. That was the background, and microtubes would have come later on. Anyway,
Okay,
please we should not.
Okay, just one. Yeah. Then I think we can start with Dr. Purushottam. Okay.
Yes, sir. I'm here, sir.
You are here, no? Okay. So after Dr. Purushottaman, then we shall go to Professor Subalkar again. Okay. So now let me tell something about Dr. Purushottaman. Dr. Purushottaman Narasimhan obtained his master's degree in 2012 and PhD in 2019 from CSIR, Central Electronics Engineering Research Institute, that is CIRI, Pilani, India. From 2012 to 2021, he also worked as scientist and senior scientist in CSIR CIRI. His field of research is vacuum microwave tubes, especially traveling wave tubes. And during his tenure in CSIR CIRI, he was involved in the design and development of KU and KA band TWTs for satellite communications. His doctoral work was based on the study of metamaterial assisted traveling wave tubes. Currently, he is working as a research associate in Lancaster University, where he is involved in the development of TWTs for 5G and 6G communications. So now, may I request Dr. Purushottaman sir to deliver his lecture. Sir, please.
Thank you, Dr. Saritpal, for the introduction, and thank you to all the organizers and other attendees for being here for this presentation. I shall share the screen. I hope everybody is able to see it.
Yes.
Okay.
Yes, it is visible.
So, good evening to one and all. The topic of today's talk is scope of metamaterials and microwave tubes. So when we talk about metamaterials and microwave tubes, initially when all this started, it just seemed like a very unlikely combination. Where do we even have these metamaterials inside? Like what kind of properties are we trying to tune? What kind of performance improvement are we trying to look at? So hopefully I'll be able to answer some of the questions today. The talk is limited to vacuum microwave tubes. It does not include any photonic bandgap applications that can be used in accelerators or other microwave tubes. It does not look at terahertz side of it. There are other researchers who are already working. Hopefully we'll have their talks later. What we are talking about is vacuum microwave tubes and how metamaterials are being incorporated in them. And when we look at metamaterials and microwave tubes, at least as far as I understand, it can either be a metamaterial based tube or a metamaterial assisted tube. Metamaterial assisted tube is something that I would consider where metamaterials are just piggybacking on an already existing interaction structure. It could be something like a helix slow wave structure, or it could be a folded serpentine waveguide structure wherein you just fill something here and there. It does not totally drastically alter the properties, but it just adds a little bit of boost somewhere here and there. Whereas metamaterial based or metamaterial inspired devices, whatever nomenclature we choose to call it, are those where the device, the complete property of waveguide or a cavity is changed by introducing some metamaterials, wherein metamaterial acts as a filling medium inside. We will see examples of both kinds of applications. So when we talk about metamaterial based microwave tubes, it has covered metamaterials of all four categories. It can be a single negative or a double negative, or few researchers have even worked on double positive metamaterials. In single negative, again, you talk about whether it is epsilon negative or mu negative. And most of the metamaterials used in microwave tubes have been limited to few structures. They are complementary splittering resonators and their variants, thin wire structures. But the reason why I have put CSRR first and SRR later is I'll try to explain later. So these are very typical metamaterial structures being explored for microwave tubes. So why at all do we go for this? There must be some reason, right? So the reason is basically some kind of performance improvement. It could be to alter the size of the structure. So I don't say exactly smaller or larger. So it is just size scaling. For some applications, we need structure to be miniaturized. For some applications, we just need it to be enlarged. We need the structure to be larger. And of course, we need some other benefit also. So predominantly, they are used to enhance gain and power, thereby electronic efficiency of your device. Recently, there have been some publications wherein they are trying to enhance the bandwidth of the device. And also, they are looking at multi-band operation of the device. So these are the main targeted performance enhancement issues. So before we could talk about microwave tubes, whenever researchers try to start with this problem area, we try to explore metamaterial structures first, and we kind of get stuck in trying to understand how to arrive at the basic properties of metamaterials. Like several eminent experts have talked before today. They were all talking about how metamaterials are changing the properties, allow us to tune the properties, allow us to give a tailor-made properties to the devices. So obviously, it will be a question in mind of what kind of properties, like how do we know what properties they have and what are the values at different frequencies. The thing is, when you're using commercial electromagnetic solvers, when you're trying to solve for Maxwell's equations using these solvers, it's a forward problem wherein you have some materials and you give the properties of the materials, be it electrical conductivity or loss tangent or permittivity, permeability, and all that. Or maybe you give some BH curves. So you give the properties of the materials and the system is solved. The electromagnetic problem domain is solved using Maxwell's equations by incorporating all these material properties. And finally, you arrive at electric and magnetic fields. And then you kind of do a post-processing. For example, if you want scattering parameters, you take the ratios of electric fields and you arrive at them. So, some kind of, performance of performance of the device in terms of S parameters. So understand how the device behaves. Whereas when it comes to metamaterials, you have the constituent materials. You might be having some kind of dielectric substrate. You might be having some kind of metallic inclusions. You know the properties of these individual materials, but you do not know the property of the complete structure. So in this case, it's kind of an inverse problem. What you feed to your electromagnetic solver is just the properties of the constituent materials. So you should be able to find a way to arrive at the property of the complete metamaterial unit cell. So your Maxwell's equation is solved by your commercial electromagnetic solver. You arrive at S parameters. And then from there, you try to interpret the properties of metamaterials. So in this case, it's kind of an inverse problem. I thought it was prudent for me to go through a little bit on the parameter extraction and just give an example of some of the very common simple methods that are available. And then we can also talk about the microwave tubes part of it. So when we look at some transmission line or like a waveguide or coaxial line, anything, this is a simple representation wherein you have 3 regions here, out of which the second region is filled with material. It could be metamaterial, which can be considered homogenized. And towards the right, what you're seeing is the electric field at different regions. So the electric field get transmitted through the region and they get reflected in the region. We have the propagation constants in regions 1, 2, and 3. And so the problem becomes solving these particular constants in the expressions of the electric field. So when we try to solve these constants subject to electromagnetic boundary conditions, we see that these constants are expressed in terms of the reflection coefficient and the phase of the transmission parameter. So here you can see the reflection coefficient is pretty straightforward here. It just depends on k0, mu0, and mu1 and k1. But phi is kind of not that straightforward because it involves an exponential function, which when expressed in terms of natural logarithm, comes out to be minus I ln phi plus 2m phi, where m is an integer. So here you can see you don't really have a well-defined value of this integer m. It becomes a branching problem. So now you might be able to understand how this could affect the parameter extraction, because you just, as a user, you would not know what kind of value this m should take so that you can arrive at your phi. And also, it is necessary to explain that the S parameters, when you kind of do some algebraic manipulation here, you arrive at the scattering parameters, which are again dependent on your impedance, and the n here shows the refractive index. So so as I said, in a commercial electromagnetic solver, you already have your scattering parameters. So from scattering parameters, you can, if you have that, then you can arrive at your impedance, and also you can arrive at some expression involving your refractive index. So again, when it comes to impedance, it seems a little bit straightforward. Once you incorporate your passivity condition, saying your impedance should, real part of the impedance should be greater than or equal to 0, and the imaginary part of refractive index should be greater than or equal to 0, you can come up with the relevant sign for impedance. Whereas when it comes to your refractive index, it's again a bit of a problem. You need to understand what sign you should give because of your branching problem. So for that, what we do is the refractive index is returned in a form like this with real part and imaginary part. And it shows that the real part is composed of the ln of this particular exponential term, and it also has a branch index given by 2m pi. Whereas the imaginary part of refractive index seems to be an easy term to compute. So our problem is imaginary term is fine, but the real term has a problem. We need to identify what value of m should be used. So the expression that might solve this problem for us is Kramers-Kronig relation. Put simply, the Kramers-Kronig relation allows us to find the real part of refractive index when you know the imaginary part of refractive index. So this p here stands for principal value of this integral. So as you can see, the frequency kind of goes from 0 to infinity. but in real case, you do not have you do not have infinite frequencies. You operate in a finite bandwidth. So the idea is that you try to implement this integral in the sum form, a summation form, and the summation is again restricted to a particular frequency bandwidth, and then you solve for that. So you already know your extinction coefficient or the imaginary part of refractive index, and from that you can get the real part of refractive index. Of course, you have to avoid a singularity wherein omega could be equal to omega dash. And since it's a truncated interval, there is always a trade-off. It shouldn't be too high to violate the subwavelength limit of your metamaterials. At the same time, it should not be too small that it leads to numerical error. So your Kramers-Kronig relation allows you to get this nkk of omega dash. And from this expression, you can identify the value of m, where n effective naught is the n value for m equal to 0. For 0 branch index value, you have some n effective. From that, you can identify this the branch index value. And once you have the branch number, you can substitute everything back into your n effective, which would be complex, just as z effective is complex, and you can finally get your epsilon effective and mu effective. The other method that you have is many of the metamaterial structures that we see, something like splittering resonators or thin wires or complementary splittering resonators, everything. They follow some kind of mathematical model. Thin wires, for example, they follow Drude model, which is given here, and splittering resonators, they follow Lorentz model, which is given here. So if you already know, if you have some a priori information of the kind of mathematical model that that your metamaterial structure might follow, but it's just a matter of finding the value of permittivity and permeability, then you can go for this iterative method. So the idea behind this iterative method is you have your scattering parameters, you have your magnitude and phase of scattering parameters from your unit cell simulation, which is shown on the right side of this flowchart. So what you do is you will see that from Drude and Lorentz model, there are about 7 unknowns here. You have to generate guesses for these 7 parameters, which they have to be in the range. From these values, you get your mu effective and epsilon effective, and you can calculate your scattering parameter from that. So now you have a scattering parameter set from the guesses, and you have a scattering parameter set from your unit cell simulation, your actual data. So now it is just a matter of matching both of them. So what value of all these 7 parameters will give you a match between these 2 curves? So that forms an objective function. So your objective function is to minimize the difference between what the scattering parameters, the S parameter curves from your guesses and the S parameter curves from your unit cell simulation. So you can use any kind of optimization technique. I have tried to use some genetic algorithm. I'm just showing you a sample result, how it kind of converges. Here you can see the red lines are from the unit cell simulation and the blue lines are from the genetic algorithm. So you can see not only the magnitude and also the phases are matching very well. So each of these curves might have several hundreds or maybe even more than 1,000 points. So the power of your implementation lies in matching S parameter curves for all those 1,000 points across 4 curves. So once you have this, then you will have all 7 parameters to be put back into Drude and Lorentz model, and you will get your epsilon and mu. So with this brief intro, the next one is we'll move on to metamaterial in microwave tubes. So one particular type of implementation that I worked on was thin wire metamaterial based interaction structure to realize a backward wave oscillator. So this is a typical thin wire structure. It is periodic along X direction and periodic along Y direction. And of course along Z direction as well, but Z direction is also the propagation direction. And along Z direction is also, since it's an interaction structure, you need an electron beam going down the structure. So the electron beam is supposed to propagate along Z direction. and the thin wire lattices are kept like this. So as you can see, this is the permittivity of this particular array of thin wires is not a scalar, but it's a tensor, wherein you have particular permittivity values in along x and y directions, and along z direction it is given by epsilon h. So if this is the case, you have a transverse permittivity along x and y directions. So this transverse permittivity is given by this expression, wherein this Kp is the plasma wave number. And the plasma wave number can be arrived at from this expression. I know that this is not normally the expression that are popularly used for thin wires, but this is a slightly modified version of plasma wave number. And we kind of observe that this matches with whatever simulations we do. So how do we? So we have observed that. So how do we implement this structure? So we start with just like any other interaction structure. This is also a periodic structure. So when it comes to periodic structure, we are interested in finding out the frequency of operation and what frequency is going to be generated. Since it's a backward wave oscillator, what frequency is going to be generated in the device. So your electron beam, for that, the electron beam should coincide at some point with your dispersion line. So we are interested in finding the dispersion curve of the structure. So as I have shown earlier, this is like a thin wire of circular cross section. We can also have thin wires of square cross section because it is easy to fabricate. Whereas circular cross section is very difficult to fabricate in this kind of mesh. So I had taken a rectangular waveguide of 22.86 by 12.8, and which is periodic in z direction. And the wire cross sections are given, and the periodicity is also given. So one might question, well, okay, why are we implementing this? Well, how is it going to change the property? We talked about metamaterial based and metamaterial assisted microwave tubes. This is a case of a metamaterial based device. So what kind of properties are going to drastically change in the waveguide? A waveguide can be also modeled as a one-dimensional plasma. One-dimensional lossless plasma, wherein instead of your plasma frequency, you have your cutoff frequency of the mode. So just like your plasma, when you operate below the cutoff frequency of the mode, you either operate in a negative permittivity region or a negative permeability region. So it can be considered equivalent to your plasma. So just like that, when you look at a rectangular waveguide and you're operating below the TE cutoff, it can be considered as the waveguide can be considered as a medium with a negative permittivity. Conversely, if you operate the waveguide below its TM cutoff, it can be considered to exhibit negative permeability for that mode. So now, once you have the negative permeability, it is only a matter of adding another negative permittivity material in order to have wave propagation. So we all know that wave propagation happens in double positive material and double negative material, whereas it is evanescent in single negative material, be it epsilon negative or mu negative. So the idea here is we need to operate the waveguide below its TM cutoff, and we need to implement a negative epsilon structure for wave propagation. So why TM cutoff? Microwave tubes, particularly traveling wave tubes, they all operate on Cherenkov radiation, or in this case, reverse Cherenkov radiation. And the electron beam tunnels down along the z direction. So
hello,
for the electron beam, yes, sir. Yes, sir.
Have you not to say something about whether the excitation is TE mode or TM mode?
Yes, sir. I was coming to it. I had mentioned TM mode. Yeah.
Okay. Please
so
go ahead.
we are, yeah.
Please go ahead.
Yeah. So we are trying to operate below the TM11 cutoff of the waveguide, and we are interested in keeping that TM mode going because we want an axial electric field. Axial electric field allows us to accelerate our electron beam, accelerate our electrons so that they can form bunches and eventually transfer the energy from onto the RF signal. So that's why we are going for a waveguide operating below TM cutoff, and we are implementing an epsilon negative structure. So this is the dispersion relation. Sorry, the legend is missing. The solid lines correspond to your lattice of circular cross section, and the dotted and markers correspond to dispersion curve of dispersion curve for the wires of square cross section. So as you can see, there is not much difference. So if you're going to go for wires of square cross section for fabrication, for ease of fabrication, it will be good, and it won't change the property much. And again, we are looking at, as I said, we are interested in knowing what will be the frequency, what will be the frequency of the amplified RF signal or the RF output. So for that, we need to, so our desired frequency is in the middle of the band, middle of the first backward mode. So since it is double negative medium, it is not going to support forward mode, it's going to support negative, it's going to support the backward mode. So this, for this particular first mode of operation, the midpoint is about 12.8 gigahertz, and corresponding to that 12.8 gigahertz, we draw the beamline here. So as you can see, this how the lattice is being repeated along the Z direction. So here you can see this is the S parameter curve of a waveguide, the TM11 curve corresponding to TM11 mode with the thin wire lattice. So here you can see the cutoff of the TM11 mode is kind of shifted towards the higher frequency, but at the lower frequency you also have a bump in the S21 curve, which is going almost as high as -5 because of your losses, because of inherent losses in the structure. So this is a very typical characteristic of a thin wire medium. Now, one might wonder, thin wire medium is just a Drude model. You do not see any resonance here. Why is there even a resonant kind of behavior? Well, this resonant behavior has been shown to come from your spatial periodicity. When you just take your thin wire as something that repeats along all three directions in an infinite way, then you just have a Drude model ideally. But when you have a finite, when you have your thin wires repeating for a finite number of periods, and you have the spatial periodicity, it has been observed that this gives rise to a kind of a resonance phenomena. So that's what you see on this very narrow peak in the S21. But nevertheless, it is good enough for us because we are not looking at any broadband amplifier. We are looking at backward wave oscillator. So this is good for us. So here is the plot showing an axial electric field here. So which is good for our electron beam propagation. So bunching can occur. And this is the magnetic field. Why I'm showing this magnetic field is to couple the electromagnetic signal here. So this is how our complete device might look like. You start with your electron gun for beam emission, and it travels down the tunnel, and you finally get it at the, you finally receive the spent electron beam at the collector. So in order to tap the RF signal, you put a loop type coupler here. Here you are going to probe the magnetic field instead of electric field, because if you want to probe your electric field, you might end up putting a probe over here, which would cause an obstruction to the electron beam. So you go with the loop type coupling. And you will note that normally for any vacuum tube like a TWT amplifier, your output coupler will be on the other side, close towards the collector, because it's a backward mode. You end up having the RF output coupling in the electron gun side. So we wanted to see whether we can fabricate this particular thin wire array and put it inside a small waveguide prototype. So we were able to do it. And many thanks are for my former colleagues from CD who were able to do this within a short span of time. Credits to Dr. Neeraj Kumar and his team, Nikita and Sahil. Without them, I wouldn't have been able to do this. So thank you so much. So you can see the square array thin wires going along this. But this is just a prototype showing the ease of fabrication, that's all. We still haven't been able to do any cold testing or anything with this. Here you can see your micro EDM at work, making holes for the pillars to stand on. This is again after the optimization of your loop coupler, you see some scattering parameters. It shows a decent amount of scattering parameter accounting for loss in the structure. So I also ran the PIC simulation for
Sir,
this. Yeah.
Hello, sir.
Yes, sir.
There's a
Yes.
relevant question coming up from Professor S. Raghavan. May I please
Yeah,
go
sure.
for the question, sir?
Yeah, sure, please.
Yeah. So there's a question from Professor S. Raghavan. This question is very much relevant for from the fabrication point of view. So his question is: our researchers in India face problem in fabrication and testing of metamaterials. Can you suggest assistance in the aspect, please?
I'm not sure exactly.
In this question, hello.
Yes.
Yes, sir.
Yes.
I think this question can be answered at the end of the lectures. At the end, because it has to be discussed.
Okay, sir. So we have in the question answer session. I'll just
This particular
go
question
through
will
the
be taken
question.
up. This
Taken
particular
up?
question will be taken
Okay.
up. Yes,
Thank you, sir.
Because
Thank
it
you.
needs a detailed discussion. Okay.
Okay,
We
sir.
can go ahead, please. Yes.
We can go ahead with in the question answer session. Thank you, sir.
Thank you. I was able to run the PIC simulation, particle insert simulation, showing the beam wave interaction in this structure. So as you can see, it produces a very clean amplification of the RF signal. This was taken at the input side of the structure because it's a backward mode. And as you can see, as we designed it, the peak signal is at 12.712 gigahertz. This is the Fourier transform on the right hand side, and on the left hand side is your amplified RF signal. This is one particular type of backward wave oscillator that we had come up with. There are other relevant works. Most of them work on split ring resonators and complementary split ring resonators. Here you can see that, the output power that we came up with is, sorry, that slide is somehow missing. The output power that we came up with is around 12.98 kilowatt at 12.712 gigahertz, and the efficiency, the electronic efficiency, was around 13%, and which is comparable to the other published works. And most of them, you can see, they either work with complementary split ring resonators or derivatives of that, or split ring resonators. And as also you can see, the frequency of operation for all of them lies in somewhere at S band, C band. And so our particular work stands a little bit distinct from all these works in the sense that we were able to push it to X band. The other part of my talk was on the metamaterial assisted helix slow wave structure, wherein I said that the metamaterials do not drastically alter some property of the interaction structure. Rather, they kind of piggyback and give a boost in the property of the interaction structure. So one such example is helix slow wave structure. So for our initial analysis, we just wanted to know if there is really any performance improvement, whether there is any scope of using metamaterials in this. Do we get any benefit out of it? So for that, we didn't want to complicate any analysis. So we just started with static values of epsilon r and mu r. And I know it violates physical property of epsilon and mu r. It has to be dispersive. But just for qualitative outcome, we took static epsilon r and mu r, and we gave the negative values. We assume that the individual support rods here, a helix TWT normally comprises of 3 support rods with a helix at the center and metal envelope outside. So we just assume that what if we replace this dielectric support rods with a negative value of permittivity and permeability, and the effective permittivity in this region comes down because of that. So we saw that with higher negative permittivity and permeability, we were getting an increase in interaction impedance, which is shown by this symbol K. And also, if there is higher interaction impedance, it means that you get higher gain, which is a good thing. But one caveat here is if you have higher interaction impedance, that also signals that you have a higher phase velocity, which means your device will have a higher beam voltage. So there is always a trade-off when we try to boost our interaction impedance. However, we had tried in a limited way with tape helix model incorporating this dispersive nature of epsilon r and mu r, but we haven't been able to come up with any concrete results saying this actually works. At this juncture, I would like to point out a very important publication in 2021 by Mr. Akhil Guha and Dr. Sanjay Ghosh from CSERCD. They were able to incorporate a particular type of metamaterial structure through design called I-Shaped Metamaterials along the support rods. So the support rods that they had taken was beryllium, and they had incorporated I-Shaped metamaterials. I-shaped metamaterials are again a derivative of your electric LC resonators, which are again somehow derived from your basic SRR structures. So with that, we were able to see an interaction impedance that is very typical of helix low wave structure. So the claim from the authors was that it allows us to have broadband with higher interaction impedance when compared to band loaded helix slow wave structure. However, they still haven't come up with any beam wave interaction simulation to prove their claim. I hope that they do it very soon. So a shout out to Raktim for an interesting article in Electron Devices. Hope you will read it. Some of the other implementations of traveling wave tubes are in folded waveguide, but to a very limited.
Purushottam,
yes, sir.
You were mentioning about the work just now. You were mentioning
Yes,
about the work of Raktim Guha.
Yes.
And that is a forward wave, and so it is not a backward wave. So it directly applies
yes,
to TWT.
Yes, sir. Yes, sir.
Yes. So not backward wave. So this is very interesting.
This is not,
very interesting.
This is not a backward wave; it's a forward wave.
Forward wave and suitable for conventional. Suitable for TWTs, not for BW backward wave amplifiers or oscillators.
So what they were trying to do was they were just trying to replace the vanes with metamaterial structures.
Please go ahead. Please go ahead.
The other metamaterial based vacuum microwave tubes, they have been explored not really that much, just as a homogenized model. Here you can see a single period of a folded waveguide slow wave structure, wherein the orange regions show some kind of epsilon negative metamaterial. They hadn't really mentioned anything about the particular type of structure that can be used. Rather, they had just taken the epsilon negative property of a Drude model based epsilon negative property, wherein they had mentioned that there is an upshift in the operating frequency range, which means at the lower frequency range, you have increased interaction impedance. And also they have claimed about 30 times the output power at around 70 gigahertz. So again, there has not been much exploration in this. I hope more come up. And there have also been several other sources like oscillators and klystrons, wherein in klystron implementations, they are not really trying to go for size enhancement. Rather, they go for miniaturization of cavities and simultaneously increase output. So there are several structures, several explorations going on in microwave tubes in terms of klystrons, gyrotrons, and windows. So these are some of the few devices that I thought I would cover. So what do I think about when I come to the end of the presentation? Metamaterial-based microwave tubes sound so exciting, everything, but it's still at a very nascent stage. There are several problematic areas to address. You have some exploration going on at the lower frequency, but once you go to higher and higher frequency, it's not that the device size becomes smaller, your metamaterial unit cell also size becomes also smaller. For example, at let's say 95 gigahertz or 100 gigahertz, which is a common frequency range of interest, your folded waveguide is kind of like 100 micron, few hundreds of micron, maybe 1000 micron depth. So within that, you have to incorporate your metamaterials. How are you going to do it? How is it going to be structurally sound? How is it going to be safe in that microwave environment and vacuum environment? And it should not become too loose, and it should not just fall off in the waveguide. All those problems are there. And of course, when we talk about implementations in high-power tubes like klystron and gyrotron, your metamaterials should also sustain the high power. When it comes to high power, you also have high losses from the metals, and you have to handle your thermal issues carefully. And also, when it comes to high power, you look at RF breakdown issues, because when you implement something like split ring resonators, you have small gaps, especially at higher frequencies. Now, we should be careful not to have RF breakdown in that. And also, when you look at the choice of substrates, metamaterials are commonly used in antennas, explored to a larger extent than microwave tubes. But in antennas, it's you see several different type of substrates being used for metamaterials. But we do not have that liberty when it comes to microwave tubes, because they have to operate at ultra high vacuum, and hence they should not be they should not have any material inside that can degas easily. And so your choice of substrates is kind of limited. And of course, as I said before, higher frequency is always an issue when it comes to both metamaterial implementation and the tube. So these are the challenges to address. Hopefully, in the coming years, we will have more and more answers to these issues, and hopefully we'll come up with some device which shows much promise. This is all from me. Thank you so much for your attention.
Thank you, sir. Thank you, sir, for such a nice lecture. Now I'll request a question from S. Raghavan, sir. The question I am repeating, sir. Our researchers in India face problem in fabrication and testing metamaterials. Can you suggest assistance in the aspect, please? This is a question from Raghavan, sir.
Sir, even back when I was in Siri, we were not able to have any particular setup for characterization of metamaterials. However, several IITs, I think they have facilities for that. We do have fabrication facilities. You can several of the metamaterials can be fabricated using your MEMS processes like Liga. And in fact, the first metamaterial structure, if Basu sir would remember, we at Siri, in fact, we fabricated our first metamaterial using just a printing technique. So we started with this, and we eventually went on to UV Liga process, which also gave us a success. So fabrication-wise, we do have facility, but characterization, they are limited to academic institutions, and maybe some other labs also might have it. I do not have much information about it, but it is feasible to set it up.
Okay, thank you, sir. So this is the next question from V. Mahadevan. So his question is, how about the efficiency improvement in case of assisted metamaterials? How about the efficiency improvement in case of assisted metamaterials? This is a question we have from V. Mahadevan, sir. Hello.
Sorry. So we do not have the definite figure of what would be the efficiency enhancement when it comes to microwave tubes. But the general idea is to improve the concentration of electric field on the axis of the beam, so that we can derive more power from it. Like I said, when it comes to other devices like Helix TWTs, we still do not have a complete analysis of it. Hopefully we'll have answers.
Hello. The interaction impedance is higher in the case of metamaterials. Yes, that would be the reason for probably the efficiency enhancement.
Yes, sir. The on-axis impedance would be higher.
And
that
I
is
think
where we are looking at.
if Ratim is around, he can give some figures also. If Ratim is around, he can help giving some figures on efficiency. Ratim Guab Siri Pilani. Yes, is he there? He can give some answer about the figure of efficiency, say without metamaterial assistance and with metamaterial assistance. If he's there, he can immediately say. I cannot say.
I am audible, sir?
Yes, you are audible.
Sir, right now I do not have that comparison table, but I can say that the researchers all over the world has tried to enhance the interaction impedance, and they shows the enhancement of efficiencies around 90% they can achieve using metamaterial assisted devices. So in the 90% electronic efficiency. Actually, the group of Dr. Duan in Chengdu, China, they have reported that work in their research paper.
Yes. Yes, yes. Yes. USTC, University of Electronic Science and Technology.
Chengdu.
Of China at Chengdu. Yes, yes, they are done. Duan's group.
Yes.
Duan. Yes.
Excuse me. If the efficiency is as high as 90%, any specific models have been fabricated for use in the market?
Oh.
Sir, actually, they have reported that work, and also they conducted their fabrication around the structure, metamaterial assisted structure. So I do not know that they have also produced that structure for the commercial use. I'm just talking about some research paper they have reported on it.
Now, once the unit is fabricated, then it has to go through extensive tests before it really gets into any system. So whether
Yes, sir.
What stage possibly it is, maybe it may be in a proto stage where the testing has to be done in detail, because 90% efficiency is a very high value.
Yes, sir. You are correct. Maybe that is a prototype.
See, if it is of this nature, there will be a lot of takers for such devices, and that too if the power is also going to be very high. So I don't know what is the order of power they are looking for at this stage.
Actually, I do not remember, but I think it is in megawatt scale.
So at what frequency?
It is around C-band or S-band.
Okay.
Thank you.
Okay, thank you, sir.
So we have a next question from Mumtaz Ali Ansari, research scholar, Electronics Engineering Department.
No, sorry.
The question is, can you comment on phase as well as group velocity for metamaterials assisted BWO?
May I just make a correction?
Yes,
Mumtaz
sir.
Ali is not a research scholar. He was a research scholar.
Okay,
He's
sir.
Dr. Mumtaz Ali.
Achha.
Now he is with IPR, Institute for Plasma Research, Gandhinagar. Please go ahead with that. Oh, sorry. Go ahead with that.
Sorry on that part. Actually, that is what's written in the message. So
that was an old figure.
Yes. I'm sorry for that. Yeah. With due correction, I like to repeat again the question. Can you comment on phase as well as group velocity for metamaterials assisted BWO?
I think I see the questions here in the chat.
Yes, sir.
So the phase and the group velocity for this, we calculated, if I remember correctly, it was around 0.5 times C. VP by C was around 0.5. And so the beam voltage is quite higher here. The beam voltage that we had was around 85 kV. But it is still comparable with several other published work, which we are looking at 300 kV, 200 kV, something like that. And as far as
sorry for interrupt. Actually, my concern is about whether it's a positive or negative. Means the thing I will ask.
No.
Okay.
This is a negative group velocity.
It is phase velocity is positive.
Yes.
Okay.
And you were asking about the number of periods. The number of periods is again the number of periods you should optimize it just so that you have enough amplification. And for the growth of the field, I'm afraid I do not have much information on the third and the fourth question. I need to look back into our simulations.
One more question is that what kind of cathode are you using? Is it thermionic cathode or something?
No. Right now we are just looking at PIC simulation. In particle cell in cell simulation in CST, if you know, it is only DC emission.
Okay.
For Richard's question.
Yeah, there's a question from Richard Joe. Could you suggest on materials to be used for high power metamaterials? This is a question we are having from Richard Joe Stancelis.
Yeah. So so when he says materials, when you look at it is highly preferable that you use all metal metamaterial instead of a dielectric substrate. Dielectric substrate backed metamaterial might be useful when it comes to applications like antennas or waveguides. But when it comes to such hyper tubes, it's better to go for a all metal metamaterial. And usually the material used is copper. And of course, when it comes to microwave tubes, you just don't use copper, use YFHC copper.
Can we use these metamaterials for like gigawatt range, like for directed energy weaponry applications?
I think you can use that's what the problem is. You have to ensure that your metamaterial structures are not too flimsy to sustain high power and breakdown. If you're able to work on that, you can always use that.
Okay. Okay. Thank you.
And the last question was, is there any periodicity condition in the NTM array? Yes, there is periodicity condition. Even in our thin wire structure, you might have seen that it is periodic along X and Y direction. I guess I have addressed all the questions.
Hello.
I'm not able to hear you, I think.
Thank you, sir. Thank you, sir, for such an informative session. I'd like to thank you on behalf of the entire BCREC institution, as well as the thinkers on the metamaterials, the research scholars, and all the attendees today. Now we look forward for our next talk. We have with us Dr. Shubol Kaur, sir, and introduction will be shared with you by. Where is it? Okay, so it's already been shared with you. Now we'd like to hear from Subol Kaur, sir. Sir, please, it's your platform now.
Yeah, am I audible now?
Yes, sir, you're audible, sir.
Okay, and presentation is, I have shared it. Have you, is it?
Yes, sir. Yes, sir.
You make it full screen?
Yeah.
Full screen.
Yes.
F5.
Full screen.
Yes, yes.
Thank you.
Is it clear now?
Yes,
okay.
sir. Thank you, sir.
Okay. So long we have heard a very highly technical talk by Purushottaman, and that too in microwave tubes. But my talk will be very general on metamaterials and metasurfaces. Practically, it will be an overview starting from the beginning of the development of metamaterials and going through different developments in microwaves and photonics, and culminating with the state of art developments till today. So, well, 21st century is the century for metamaterials and metasurfaces. Interestingly, metamaterial was first fabricated in 2001 in UCSD, USA. And for last 1 decade, the planar version or 2D version of metamaterial known as Metasurface has revolutionized the photonics research. Initial development was at microwave frequency because it was limited by fabrication technology available in those days. But nowadays, with nano fabrication technology, we have excitingly new vista of applications in photonics too. Well, it was V.G. Veselago in 1967. Original paper was in Russian and it was translated in English and published in 1968. He showed that solution to Maxwell's equations in hypothetical media having simultaneously negative isotropic permittivity and permeability can produce some counterintuitive phenomena like reversal of Snell's law. That is, in left-handed material or metamaterial, it goes in the negative theta direction. Reversal of Sedan radiation, when a particle moves with very high velocity, it gives rise to an electromagnetic radiation cone, which is called Sedan radiation. In normal material, the Sedan radiation and the particle moves in the same direction, but in metamaterial, the Sedan radiation moves in the minus z direction. So this has a lot of advantages for accelerator designers. Also, there is reverse Doppler effect. We all know about Doppler effect, and this reverse Doppler effect has promising applications for radar. Well, at first I shall discuss metamaterial analysis applications at microwave and higher frequencies. Let us see very briefly. This is for a normal material where this lattice constant P compared to lambda. Lambda is very, very large compared to P. In photonic crystal, lambda is comparable to P, but in metamaterial, lambda is greater than P. Typically, it is 10 times of P that people normally use in metamaterial design. Metamaterials, also phenomenologically known as a left-handed material, but technically and also popularly known to make things invisible. Technically speaking, LHM is artificially structured material, commonly metal dielectric composite, having extrinsic inhomogeneity to an incident electromagnetic wave. It is effectively homogeneous. The structural properties, rather than the chemistry of the material with which it is designed, determine the characteristics of LH materials. LHMs are realized with unit cells and periodic structure, having unit cell dimensions commensurate with small-scale physics. During last 2 decades, R&D in metamaterial have realized exotic functionalities not available in nature, including commonplace applications in antennas, filters, couplers, and at microwave and higher frequencies. Why this metamaterial is known as left-handed material? Reason is this: in normal or natural material, E, H, and K triad makes a right-handed triad, where electric field is this, magnetic field is this, and the Poynting vector or the energy carried by group velocity is in positive z direction. But in metamaterial or left-handed material, EH remaining the same, even P remaining the same, the K vector or the wavefront vector moves in the minus z direction, resembling the concept of backward wave. But Poynting vector cannot be in negative direction, negative z direction, whether it is in right-handed material or left-handed material. It remains in the positive z direction, otherwise causality will be violated. Now let us see what is the position of metamaterial in the quadrants of the plot of permittivity versus permeability. Here is D and G double negative or metamaterials, where both epsilon and mu are negative. So N is minus square root of epsilon mu, and the refracted ray goes in the other direction, towards the negative side of the normal. But double positive material, epsilon is greater than 0, epsilon and mu both are positive. These are our conventional material or natural material. But if epsilon is negative and mu is positive, then we have plasma and fine wire structures. For your information, our ionosphere is known to exhibit negative permittivity. All right. But as far as the negative permeability is concerned, this can be realized with microstructured magnets and split rings. Well, who are the visionaries for these metamaterials? First, we have to mention the name of James Clerk Maxwell. This is the Maxwell's wave equation. And we find that n square appears in Maxwell's wave equation. So Maxwell's wave equation is equally valid for signal propagating both in case of right-handed material and left-handed material. This is very interesting. Well, we have to mention the name of Sir J.C. Bose. His research on twisted jute pair structure back in 1898, used as polarizer, was essentially artificial chiral materials we know in today's terminology. But as far as metamaterials are concerned, P.G. Vasilago is the father figure. His theoretical investigation indicated the reversibility of Snell's law, reverse Doppler effect, and reversal of Cherenkov radiation for metamaterials structured with simultaneously negative permittivity and permeability. And this J.B. Pendry is again a great figure in metamaterial because he was the first who was able to realize negative permittivity with thin metallic wares in 1996 and matrix of split ring resonators in 1999 to realize negative with thin wares, negative permittivity, and with matrix of split rings, negative permeability. Here, let me mention that epsilon is shown to be epsilon are effective and mu has been shown to be mu are effective because unlike natural material, metamaterials exhibits bulk properties. It is the bulk property that gives the metamaterial characteristics, and unlike the natural material which exhibits the elemental properties. This has to be remembered in case of metamaterials. As I mentioned earlier, first metamaterial was developed at UCSD US in 2001, and that was of plasmonic type. What do you mean by this plasmonic type? Negative permittivity is realized with an array of metallic thin wares like this. This is a dielectric substrate on which this metal thin wares are being imprinted, and this is the periodic structure, 1D periodic structure for thin ware array, and negative permeability is realized in plasmonic metamaterial with split ring resonator. This is split ring, and this is the matrix of split ring, and again this is the dielectric substrate on which these metallic split rings are printed, and this is 1D SRR matrix. Each unit cell in such periodic array of TW and SRR, when irradiated with an electromagnetic signal, acts respectively as an electric atom and magnetic atom, mimicking the atomic arrangements as in the lattice of natural material. This is very important. In these artificial materials, we have segregated electric atom and magnetic atom with the help of thin ware array and SRR matrix. In subsequent slide we shall show, or here we can see that thin ware and SRR structures have been combined together, and they together exhibit the plasmonic metamaterial characteristics. Unlike in natural material, where electric atom or magnetic atoms are not segregated, they are in the same system. Well, when we are talking of plasmonic metamaterial, another type of metamaterial we need to talk about is the transmission line metamaterial. Recognizing the analogy between the LH waves possible with dual of the normal transmission line and similar backward wave already known since 1940s from the days of traveling of tube to exist in periodic structures, Aleftherer et al. And Olnian and Kalos almost simultaneously proposed in 2002 the realization of periodically loaded transmission line, PLTL. This is periodically loaded transmission line, which is practically done by periodically loading a host transmission line with series capacitance and shunt inductance effective metamaterial property is realizable only when the unit cell dimension P satisfies the condition P less than lambda, maybe 1/10 of lambda. This shows transmission line metamaterial characteristic chart. This is the right-handed material, normal transmission line, and this is left-handed material, just the dual. This is the dual of this one. And we can see it gives propagation constant negative, phase velocity negative, group velocity positive definitely, and refractive index negative. Interesting to note that for frequency dispersive epsilon and mu from Poynting's theorem, the expression for energy is this. Even when epsilon and mu becomes negative, as in metamaterial, their spectral derivatives remains positive, hence causality is not violated. This is important point to note for metamaterials. This is the first metamaterial, PLTL metamaterial that was fabricated in 2002. Why people are interested in transmission line metamaterial? Because being non-resonant, PLTL exhibits simultaneously low loss and broad bandwidth, and are thus well suited for RF and microwave circuit applications. Now I shall briefly go through our metamaterial research that we did at Calcutta University long back during 2006 to 2012, and we made the first plasmonic metamaterial, which was made with labyrinth resonator. This is which is little modification of split ring resonator. Split ring resonator, there is only one cut, but in labyrinth resonator there are two cuts, so that there is no problem of bi-anisotropy, which is the problem with SRR. So we made this 1D periodic structure with labyrinth resonator matrix and thin wires, and this is the combined structure. This was showcased at National Theme Meeting at Berk, Mumbai, because we did this research as a collaborative research of Calcutta University, Samir Kolkata, and Berk, Mumbai. And this was published online on 20th August 2009 with the heading India Joins the Metamaterial Club. This appeared as a news clip in Nature India. Here is the website, you can go through it. Anyway, what we did is this. We made this metamaterial. We cut out a prism of metamaterial. We studied it in a anechoic simulated environment, and we got our analytical result was negative refractive index of -1.84 at 31.25 gigahertz, and experimental results showed negative refractive index of -1.89 at 30.85 gigahertz. This was in 2009, right? Then our students, I am only I was so-called guide, but our students have done all these works. What they have done here is design of a filter. They made this metamaterial filter with CR-LH structure, and they compared their performance with edge-coupled bandpass filter, and it is seen that insertion loss is much lower at CR-LH bandpass filter, and as far as the harmonics are concerned, these are suppressed up to 10 gigahertz, whereas the same filter designed with edge-coupled bandpass filter shows second and third harmonics. An important thing is that it gives a lot of size reduction, 67% size reduction. So this was published in this journal. So whole credit goes to our student. Next comes another work on antenna. This is with CS RR. There is complementary split ring resonator. Again, work of our students. This shows the surface current. This is the fabricated structure. This is the CSRR loaded patch antenna, and this is the normal patch antenna, and this has 24% size miniaturization with pretty good antenna characteristics. We have also studied different types of this magnetic metamaterial inclusions, like multiple split ring resonator to have large magnetization, this spiral resonator, and the one with which we designed our metamaterial, labyrinth resonator. Why we prefer labyrinth resonator is this, and many designers on with metamaterial, even for microwave tube designer, can think over this, that LR structure has better bandwidth. These are all resonance structures, true, but this has better bandwidth compared to multiple split ring resonator and spiral resonator. Definitely much better than single split ring resonator. And another thing, its radius, its physical dimension is quite large compared to these two structures. So when we go for high frequency applications, this will be a better structure for designers, because this will allow you better tolerance of design. This is the reason why we used LR structure in our design, and many designers prefer LR for these two characteristics. This is again our work, again by my students, and they were all my BTech students, and they are now doing good work abroad. Another study we made is regarding variants of SRR. One is two-turn split ring resonator, TTSR, and non-bianisotropic split ring resonator, NBSR. This is TTSR and this is NBSR. This is our design structure. These are the characteristics, and we find that they have much better performance as far as non-bianisotropy is concerned. When phase of this, when the polarization of the signal becomes an important issue, one has to use this NBSR, because this non-bianisotropic, right? We have also worked with both theoretical and experimental studies on thin wire structures. This is the fabricated structure. This is the model on which we made our contribution in design of this thin wire structures. We use this loss factor method, and this is the experimental analytical, very good match, and this paper is highly cited, I find, in literature. We have also worked with 2D LR cutwire structure. This is the LR cutwire structure. This is the fabricated structure. This is the experimental arrangement. This is the network analyzer output, giving an N of the order of minus negative refractive index of minus 1.68, and this shows its this computer simulation result. We have also worked with leaky wave PLTL antenna. Advantage with such metamaterial antenna is that you can make your lobe to switch from left to right at your will with the designer parameters. This is very important for antenna designers when they use metamaterials. Many other reports are there in literature regarding low profile omnidirectional antenna, broadband bandpass filter, patch antenna using SRRs, backward wave directional couplers, and so on and so forth. People are also designing terahertz sensors using metamaterial, taking inspiration from metamaterial. Here is one of the structure in which again you can see a square type vertical LR structure, a number of them here, and with this they have been able to, because using terahertz signal, the sensing action is determined in terms of the resonance of various molecular vibrations in the sample to be sensed. So by using this, they have got very good improvement with this terahertz metamaterial sensing. People are also using metamaterial sensors, using bi-material sensors with metamaterial absorbers for sensor design. Details are available in this reference. All right. Now let me tell a few words about the exotic application potential of metamaterial. This is quite important. Super lens or sub-wavelength imaging, overcoming the well-known diffraction limit of conventional optics, supposed to be the possible due to evanescent wave growth in LH media, is gaining enough enthusiasm which might one day make it possible to image individual strands of DNA. Look, whatever imaging we do using our normal material and normal imaging techniques, it can go down to a wavelength, but not sub-wavelength imaging. But with metamaterial, we can do sub-wavelength imaging, and people are working at Berkeley Lab on the sub-wavelength imaging, and they are claiming that they can, in coming days, they can image individual strands of DNA using this sub-wavelength imaging. I will talk about that a little more in subsequent slides. Another very important exotic application is cloaking of objects. May not be of the Harry Potter type at the moment, but this is opening up new possibility of making reliable optical memories for new generation computers and showing new avenues for stealth technology. Reverse Cherenkov radiation, as I mentioned, which is opening up new applications in accelerated design, particle accelerated design. Well, a few words about super lens and sub-wavelength imaging. We know that by lens we normally understand either it is a convex or a concave lens that converges the wave or that diverges the wave. But metamaterial is something which can realize converging wave with plane slab. This is the plane slab metamaterial. On both sides of RHM. Because the it reverses Snell's law, so when it comes from right-handed material to left-handed material, it goes in this direction. So it creates two foci. One is inside the metamaterial, another is in the right-handed material on the right-hand side. So from object point to image point, we can bring the information through this left-handed material, and that can happen provided evanescent waves are not being lost. We microwave engineers know that when a signal originates from the object, there is propagating wave and evanescent wave. But evanescent wave decays very quickly and it cannot reach the image point. But metamaterial has been found to have some property which is called evanescent wave growth. Some people say evanescent wave amplification. The later term is not acceptable. It should be evanescent wave growth, which goes on replenishing the energy being lost by evanescent wave which can be understood with this diagram. With plasmonic metamaterial, we say that surface plasmons are there on the surface of the metamaterial, and that permits surface plasmon polariton to maintain a SPP standing wave, which helps the evanescent wave through resonant tunneling to get the replenishing energy, and when it comes out at the image point, we have the evanescent wave signal available. Due to this evanescent wave growth caused by resonant tunneling and assisted by surface plasmon. So this gives the evanescent wave growth possible in with plasmonic metamaterial. But a point of caution, the loss in the material might eat up the growth process. In the subsequent slides, I shall tell about that. We have some research work on that. If that is not done, if you cannot do that properly, the growth process, then the whole focusing will be smeared, and you will have a very smeared image. These Berkeley peoples have designed hyperlens based on diffraction-free superlens capability. It is able to magnify sub-diffraction limited objects and project the magnified images to the far field with conventional lens, possible application in nanotechnology, photolithography. Here is a little bit of theoretical work done by our student on super length or sub-wavelength imaging. I'm not going into the details because this is given in this paper. If I go into the details, it will be very exhaustive one. But anyway, let me go to the curves. This shows effect of loss in metamaterial design. The plot showing the effect of loss on the growth of evanescent wave in the metamaterial plane slab. Increasing loss dampens the growth of evanescent wave via LHM. You can see that, all right? This is the growth. This is the growth. But if the loss becomes quite large, then there is no further growth, and you cannot have evanescent wave growth, and on the other side, you will not have the signal. Again, the response to an impulse excitation of LHM slab with loss can reveal the quality of imaging. With the increase of energy dissipation factor delta, the sharpness of sync function decreases and the image is smeared. So this is another study which shows that more of loss will smear the image. This is another study which shows that the thickness of the metamaterial slab has got to say about the growth of the evanescent wave. As for example, this C has a better growth compared to A and B because it is much thinner compared to these two slabs. Now let me come to another interesting application of metamaterial, that is cloaking and stealth technology. Now, in simple terms, what is this cloaking? How we can make things invisible? Let us understand in simple terms. Something becomes visible because when a signal goes to the object, there is some reflected signal, there is some transmitted signal, and maybe there is some signal absorbed in the object. But with negative refractive index, with proper tailoring of negative refractive index judiciously, if we can make some such situation where there is no reflection, no transmission, as we understand as microwave or electromagnetic engineers, and also there is no absorption, the signal just glides past the object, then the object will be invisible. All right, this is the basic idea of cloaking. This was the first microwave cloaking done by D.R. Smith's group in Duke University in 2006 at microwave frequency, but this was not pretty good because this was not capable to make a 3D cloaking. Later on in 2009, Xiang Zhang's group in Berkeley lab made carpet cloaking. This is for hiding microscopic objects, and lot of research is going on this cloaking topic. I'm not going into the details of that anymore, but the references I've given that will give some glimpses of that. Now let me talk, say a few words about reverse Sedan curve radiation. So this is our split ring structure, square structure. This is a matrix of that. This has been loaded in a waveguide. This has been this diagram has been taken from the Argonne and Wakefield Accelerator Group, Argonne and Illinois Institute. They have made this metamaterial loading in waveguide, and they have found that with the help of this, they can change the beam dynamics in the accelerator. All right. So this is a quite involved subject for accelerator physicists. But for our popular applications, let me talk about another very simple but very important application. This is our work, basically work by our students. We have taken a waveguide in which we have made this sheets of LR structure matrix loading, and by doing that, by properly manipulating the structural dimensions, what we can do, we can include some some stop band in the passband of the waveguide. This one shows here. We have introduced a stop band, or this is another stop band in the passband of the waveguide. So this can act as a notch filter. Or what we can do, again with design manipulation, in the stop band of normal waveguide, we can introduce the passband. So this will be very useful for waveguide based component design for microwave engineers, right? Now I go to, this was a few words about metamaterial applications in microwaves. Now let me go to metamaterial applications in photonic developments, because now most of the research on metamaterial is aiming towards photonics. The photonic metamaterial that demands a different set of electric and magnetic inclusions or artificial atoms compared to those used at microwave to terahertz frequency. Reason is, metal does not behave anymore as conductor at optical frequencies, rather beyond 200 terahertz. So what is the solution? Solution is we go for cut wire and fishnet structure. This is a very quick glance through of megahertz to terahertz metamaterial. This was the Swiss roll structure. This is again this split ring and wire structure. Another some structure at 100 gigahertz. When we are going to terahertz, it is becoming something different. So these are different works people have done. But when we go to photonic metamaterial or metamaterial at optical frequencies, the whole philosophy of design changes from microwave thin wire and SRS structure or its variants. Here is the cut wire structure. In cut wire, pairs of metal nanostrips separated by dielectric spacer. Antiparallel current flow in the pair results in magnetic resonance. Parallel current flow in the same strip causes electric resonance. This is the philosophy. But in this structure, difficult to get overlapping negative permittivity and negative permeability. So next development is fishnet structure that combines magnetic coupled strips to provide negative permittivity over a broad spectrum, hence overlapping frequency zone for simultaneously negative epsilon and mu is essentially obtained at optical frequency. This is the Fishnet optical metamaterial designed by Berkeley Lab Peoples in August 2008. 3D optical fishnet metamaterial by using focused ion beam milling. Refractive index varies from minus 0.63 at 1200 nanometer to minus 1.23 at 1775 nanometer. This is the fabrication structure. Reference is given in my reference list. Now, another step jump in metamaterial development. Metamaterial was considered to be material-like, that is, one with tolerable constitutive properties. So far, people are talking about metamaterial in terms of tailoring the permittivity and permeability. And that this was in the initial phase of metamaterial research. People are also doing that, right? But metamaterial research has gone much further. A paradigm shift in metamaterial research philosophy has taken place subsequently, and metamaterial is now considered as a device where the hybridization with functional agents bring new functionality, and the response becomes gain-assisted, non-linear, switchable, and so forth. Thus, we now have metamaterial fueled lasing spacer, in which the emission in a spacer is fueled with the plasmonic excitations in an array of coherently emitting metamolecules. I shall talk about that. Metamaterial carbon-based nanotubes that exhibits an order of magnitude higher non-linearity compared to bare CNT, leading to high-speed switching possible at optical frequency. Transparent metamaterial made entirely of dielectric materials might make possible for interconnecting circuits using photon instead of electrons to process and transmit data, and also paving the way for light sources at single photon level. Metamaterial is going much further from its initial developments. Let me first talk about metamaterial fueled lasing spacer. The invention of the spacer, there is surface plasmon amplification by stimulated emission of radiation, also called plasmonic laser. In normal laser, it is the photons that takes care. But here the surface plasmon that takes care of the lasing action led to the development of thinnest possible laser. Here the light quanta photons of the laser is being replaced with electronic excitations at the surface of metals called surface plasmon, which can have atomic scale dimensions. However, a spacer produces very little light, and that light is not collimated into a narrow beam. So what is the way out? But if the emission can be fueled by a plasmonic excitations in an array of coherently emitting metamolecules, going back to SRRs, supported by again medium, the quantum doped radiation losses and joule losses in the metal structure of the metamolecules, we have the lasing spacer. In contrast to conventional lasers that operate at wavelengths of suitable natural atomic or molecular transitions, these lasing spacers' emission wavelength can be controlled by metamolecule design. Lot of liberty to the designer. Very interesting and very important for newcomers in the metamaterial research. Being the thinnest down to 100 nanometer laser, the lasing spacer promises new applications ranging from displays to high-speed communication and beyond. Here is metamaterial fluid lasing spacer. See, in the lasing spacer, identical plasmonic resonators forming the metamaterial array impose the frequency at which the device will lase, drawing energy from a supporting gain substrate. Here is the metamaterial array of splittering matrix, right? This combination of artificial classical electromagnetic resonators, these are, plays the role of the active medium, the lasing spacer, just as an assembly of essentially quantum inversely populated atoms plays the same role in a conventional laser. Very important. In a conventional laser, the direction of emission is dictated by the external resonator, and its coherence is underpinned by the stimulated emission of atoms in the gain medium. In the lasing spacer, the direction of emission is normal to the plane of the array, where strong trap mode currents in the plasmonic resonators oscillate in phase. Now we come to metamaterial based CNT. CNTs are one-dimensional systems with diameter of a few nanometers and length of the micron scale with unique nonlinear optical properties. Single-walled CNTs rolled from a graphene sheet are direct gap semiconductors with absorption spectra dominated by exciton lines. Possible technologies uses include nanoscale light sources, photodetectors, and photovoltaic devices. Indeed, the developments of photonic all-optical data processing circuits depends on the availability of fast and highly responsive nonlinear media that react to light by changing their refractive index and absorption. This is difficult to deliver in nanoscale size devices using electronic and molecular nonlinearities, where strong responses often come at the expense of longer reaction times and where the optical path through the nonlinear medium is shorter than the wavelength of light. Thus, recent experiments show that the nonlinear response of CNT can be strongly enhanced by adding a metamaterial layer. Single-wall semiconductor carbon nanotubes deposited on metamaterials exhibit an order of magnitude higher nonlinearity than the existing strong nonlinear response of the nanotubes themselves due to a resonant plasmon excitation interaction making ultra-high speed switching possible at optical frequency. Also, the metamaterial environment allows one to spectrally tailor the nonlinear response. These are some of the results. I'm not going to the details of that. Yes, another very important issue is transparent metamaterial. This under development can make possible computer chips and interconnection circuits to use photonics instead of electronics to process and transmit the data, representing a potential leap in performance. Unlike conventional metamaterial that use noble metals like gold or silver, these new metamaterials are made entirely of dielectric metamaterials. I mean dielectric materials, so insulators and non-metals. In fact, everything will be in silicon platform, making integration of electronic and photonic devices on the same chip. The absence of metal in the metamaterial design will save light from getting unnecessarily lost as heat in the photonic device and interconnections. In computers and consumer electronics, we'll use normally we use copper wires between different parts of the chip. But if we can confine light to the same size as a nanoscale copper wire, then we can have much faster clock speed and hence enormously fast data processing. The transparent metamaterial can make this precisely possible. Here is the innovation in transparent metamaterial lies in modifying the phenomena of total internal reflection, the principle normally used in light guided in optical fiber. Look at these figures. Here the optical momentum of evanescent waves is controlled as opposed to conventional photonic devices which manipulate propagating waves. This dramatically reduces the crosstalk. This is in conventional TIR and this is in relaxed TIR, in which this was coupling, right? Now it is done like this. You have manipulated like this. So, which manipulate propagating with this dramatically reduces the crosstalk mutual coupling among close by devices compared to any dielectric waveguide, slot, photonic crystal, etc., allowing dense photonic integration possible. The introduction of engineered anisotropy permittivity tensor in the momentum of the cladding realizable as transparent metamaterial brings about the phenomena of relaxed TIR. Here is some of the studies from that paper. Again, this is quantum information such as quantum cryptography, quantum information storage, and optical quantum computing demand effective stable sources of single photon and nanostructure to control the quantum dynamics of these photons. And I'm not going to the details. This reference is given. This is done with a metamaterial having hyperbolic dispersion characteristic, which enhances it by 2 orders of magnitude of single photon emission in such structure. Single photon sources may also be application in nanochemistry to control chemical reactions at the level of individual molecules, biochemical analysis to determine dynamics and molecular configuration, decoding DNA, and so on. So that was about metamaterials. If you permit me a few more minutes, then I shall quickly go through metasurfaces and its applications in nanophotonics. Metasurfaces are ultra-thin 2D arrangement of sub-wavelength size building blocks of metallic patches or dielectric etching. If I go to the this is metamaterial and this is metasurface. Being 3D metamaterial difficult to fabricate with, while metasurface being planar are easy to fabricate and can be easily integrated into other devices, which can make them salient features for nanophotonic circuits. In the past few years, metasurfaces have achieved groundbreaking progress, providing unparalleled control of light, including the construction of arbitrary wavefronts and realizing active and nonlinear optical effects. Unlike metamaterials, a metasurface affects incident electromagnetic waves through modified boundary conditions caused by its scatterers of which it is made up, instead of using the bulk effective constitutive properties of metamaterial. This is a very important difference between metamaterial and metasurface, which is implicit from here. Here we have negative permeability structure, negative permittivity structure, but here the wavefront is controlled with metasurface with the control of the boundary condition. It can control the wavefronts. It also resembles frequency selective surface. However, the periodicity and element structure of the former, that is FSS, is of sub-wavelength extent, while that for the latter, for metasurfaces, periodicity is of sub-wavelength extent, but for FSS, it is half wavelength order. Here are some applications. In absorbers, people are using metasurface. I'm not going into much details. In transformation optics, people are using metasurface. In thin lens design, they are using metasurface. Yes, this is last but not the least. We have talked about cloaking in 2006 and 2009 by D.R. Smith's group and Jiang Zhang's group. But nowadays, people are using skin cloaking using metasurface, and this is able to cloak three-dimensional objects. So this is the latest development of cloaking using skin cloaking. And also there are leaky wave metasurface antennas, very exhaustive subjects. Finally, I will make a few comments. Metamaterial in 2001 started with its signature property of negative refractive index. However, it has now come a long way and behave as a device that enables switchable, gain-assisted, and nonlinear functionalities, including the Metamaterial-inspired design of size miniaturized and efficient antenna, filters, couplers, etc. Although MTM already have revolutionized the research prospects from microwave to optical domain, their performance has been limited by their inability to function over broad bandwidths at optical frequencies. Designing a metamaterial that works across the entire visible spectrum remains a considerable challenge. The negative index of the NTM is due to the resonance of the individual meta atoms. This property makes metamaterials inherently dispersive. Thus, the electromagnetic properties of such materials are highly sensitive to the changes in the operating frequency, making such materials to operate only over narrow bandwidth in optical spectrum. In metasurfaces, however, the dispersion characteristics can be engineered with the proper design of its individual scatterers, and hence broadband operation can be realized. Practical optical MTM need to be 3D periodic structure resembling checker cube puzzle. Thus, typically require multiple stacks of material layers, which leads to extensive losses and also brings about a lot of challenges in nanofabrication. Many MTMs consist of complex metallic wares and other structures that require sophisticated fabrication technology and are difficult to assemble. Metasurface, on the other hand, are basically a flat periodic array of surveillance scatterers that can be viewed as a diffraction lattice. Thus, unlike MTMs, here the wavefront dynamics is controlled by boundary conditions rather than the constitutive properties of the metamaterial. Being 2D, that is planar in nature, they can be fabricated with planar technology, minimizing loss, and can be easily integrated with other devices, making them attractive for nanophotonic circuits. Last but not the least, current MTMs are typically characterized by P by lambda is equal to 1/5 to 1/20th, where P is the lattice constant. Although refraction phenomena dominate in such MTM structures, diffraction scattering affects the purity of refractive index, thereby diffusing the focusing spot and increasing the transmission losses. To obtain pure refractive phenomena, it is necessary to homogenize the MTM, that is to decrease the structural feature P by lambda by 1 order of magnitude or more. If this challenge is met, MTM will behave as real artificial materials. That is, the unit cell of MTM would be so small that they would really behave like atoms in natural materials, and would be capable of producing truly homogeneous macroscopic response, thereby faithfully mimicking the macroscopic response of natural material. Here is the comprehensive list of references. Whatever I have talked here, I have skipped a number of slides, lot of details. Here is the exhaustive list. You can go through that and you will find lot of interesting things to go into the depth and get a number of avenues for metamaterial research, which is a really emerging field of research in microwaves and photonics. However, finally, I have to say, as I say everywhere, miles to go and miles to go before I sleep. I quote from Robert Frost with my own explanation of his poetic expression. The woods are lovely, dark and deep. So what happens to us when we find some success? We think, okay, this is enough. I have got a lot of things done. So, woods are lovely, dark and deep. So we sit there. But the poet says, but I have promises to keep. Yes, we all have promises to keep. We have to go a long way. And thus, miles to go before I sleep, and miles to go before I sleep. So, even before this inquisitive and erudite audience, I myself say that yes, miles to go before I sleep, and miles to go before I sleep. We have done nothing as yet on metamaterials and metasurfaces. We have to do a lot in coming days. With these few words, I thank you all for your patient listening. Thank you.
Thank you, sir, for such a nice, informative session and such a nice words you shared with us. It was really very enlightening for all of us, the research scholars, all the attendants, the faculty members, those who have joined this session. This very valuable session for them all. Thank you, sir. Sir, with due permission, there are a few questions.
Oh, definitely, sure.
Thank you, sir. Thank you, sir. I'll just read out the question.
Sure.
We have a question from Jayant Joshi, sir. Is there any relationship between periodicity of MTM and interactive impedance?
Look, in that direction, I have not worked. This is the answer to be given by people who are working on tubes and using metamaterials.
Yeah.
I cannot answer that. Sorry.
Ruktim, can you come forward, and if you can illuminate on this point? Raktim Guha, please. Mr. Raktim Guha.
Am I audible, sir?
Yes.
Can you repeat the question once?
Yes. Certainly. I'll go. Is there any relationship between periodicity of metamaterials and interactive impedance?
Interaction impedance.
Interaction impedance, yes. Sorry.
So actually, in our study, in some research work done by the research worker in other countries, they have shown that especially for backward wave oscillators, they started with all metal metamaterials. They have found some very high interaction impedance in comparison with the conventional ones. In their case, the periodicity is high. Means periodicity is very bigger than the conventional ones. Actually, they have considered a split, say, complementary split ring resonator, and they are the outer dia of this metamaterial is around outer radius. I think it is around 30 mm, and the periodicity lies in between the 40 to 50 mm. So therefore, in our comparison study, we have get some result that the periodicity of the metamaterial is for metamaterial assisted microwave tubes, it a little bit higher than the conventional ones, and it is also we get that the interaction impedance is also high for metamaterial assisted microwave tubes than its conventional counterparts.
Thank you.
Sir, we have another question. This is a question from Priya Sharma. What are the applications of photonic fishnet structure? What are the applications of photonic fishnet structure? Thank you, sir.
Okay. Good. Let me go to the fishnet structure. This is the fishnet structure, right? Here we can see that